We're starting chapter 12. Now, we've marched through this entire book with the exception of which chapter? And condensation, evaporation. Just wasn't time to do that. It's a shame, but that's the way it is. Homework for tonight. Today we start radiation. And I have to admit, today's class is a little boring because it's mainly just definitions. But you need to establish the language in order to understand what we're doing. And radiation has its own language. So let's get started. Radiation is the third and final mode of heat transfer. We have studied convection, we have studied conduction, and now we're going to study radiation heat transfer. Okay. Let's take a body. Some body, looks like a kidney. It'll be at some temperature T1. And surrounding this body is a void. There's nothing here. Nothing there. No gas, no solid, nothing. Sort of like in space. And then there's surrounding that some body at T2. And we know in this empty void that there can be heat transfer between body at 1 and the body at 2. And that is radiation heat transfer. Nothing touching the body, so there's no conduction. There's no gas, no fluid, so there's no convection. All right? No conduction, no convection. Before the more modern theories that seem to work pretty well regarding radiation came into being, how did you figure out that heat transferred from one body to the other? Anybody know? Anyone? Through the ether. You ever heard that? The ether. There was this mysterious substance you couldn't see, feel, or measure, but it was there. It was called the ether. And it transferred heat from one body to another. Well, today we don't believe in ether. There are two approaches to radiation heat transfer. The first is wave theory. Now, what's interesting about this is we actually use both of these. Wave theory. And wave theory basically says that radiation is consists of electromagnetic, I can't say it for some reason, electromagnetic waves. Electromagnetic waves, and of course we all know about electromagnetic waves. And the energy is converted to these waves. Then can move through the ether from one body to another. There's no need for actual physical conduction, or some other physical components such as convection. Also, the theory says that the energy travels at the speed of light. which C, which is equal to 2.998 times 10 to the 8th meters per second. Okay, pretty fast. And it's a function of the wavelength. Which we'll symbolize by lambda. All right. And we define wavelengths and speed of light, c, being equal to lambda times nu, where nu is equal to our frequency. And this is the speed of light, by the way, in the back. It's a little slower. It's making its way through things. So wave theory is one approach. The second approach is particle theory. And this should not really be new to you because you covered this in physics, correct? Covered this in physics? Physics 2? Right? All right. Well, let's just assume that you covered it in physics 2. Particle physics, or particle theory, is the relatively new approach. Now, the wave theory was developed in the 19th century. Particle theory was postulated and began in the latter part of the 19th century, and then really took hold in the early part of the 20th century, when you had people like Einstein and Helmholtz, Niels Bohr, all these folks. This was the golden age, if you want to call it, of physics. So this is, this is also described by quantum theory, quantum mechanics. And this theory says that radiation travels in little bundles of energy. And what are these little bundles of energy called? What? They're called photons. But they're also sometimes called quanta, I think. So, but we'll call them photons. There are bundles of energy called photons. Which, by the way, and conveniently, follow what path?
Straight line.
No, waves. They go in, the photons follow waves and have a frequency. So the two theories blend together. There's bundles of energy, and these are known as photons. All right? And the photon's energy is described as h times nu, its frequency, where h is known as Planck's constant, and that's equal to 6.625 times 10 to the minus 34. Get some really big exponents in this stuff. Joule second per molecule. And we'll go back to some of these words later. Now, let's talk about radiation's key attributes as we're going to study in this course. All right. We're going to characterize our radiation with two parameters, frequency and the wavelength. Keep in mind that this is the second time we've used nu. This is not kinematic viscosity in this case, this is wavelength. So it's characterized by frequency, nu, and wavelength. Lambda, okay? Frequency and lambda. And of particular importance to us is lambda, the wavelength. I'd like you now to open your book to page 736. And I want you to look at figure 12.3. This is one of the things that I want you to take away from this block of instruction. Radiation is emitted, a term we're going to define in a moment, at a huge spectrum. Spectrum being the wavelengths, okay? And it's very important, it's very interesting to understand that. Now look at figure 12.3. You see that little teeny block in there? Okay? What is that? You got the red block, all right? And what is that little small block in there? It's the visible range. Now, what's really interesting about this for a second, think about us. All right, what do the eyes do? They absorb and interpret electromagnetic waves. That's what they do. Really very interesting. Okay. Now, there are other devices that absorb and detect electromagnetic waves at different wavelengths. Our eyes are uniquely suited to absorb, detect, and interpret what we refer to as the visible spectrum of radiation. Okay. Now, let's take, of course we can't see at night, can we? All right, no, because the sun's not around. But can other devices see at night? Night vision goggles? You've all seen those little blurry green images? Well, they are detecting what?
Infrared.
They're detecting the thermal radiation, typically the infrared zone, heat signatures of whatever is out there making a heat signature. And there are lots of applications for that. If you can go to the Home Depot and you can rent this device, kind of like a gun, and you can shine it all over and you can see different heat signatures. All right? Typically used by your person who comes out to check your house to see where heat is leaking out of your house in the winter. Okay? Very interesting. All right? So we see only a small amount. If you look, you see the X-rays. In that area, you see gamma rays. You see the microwaves, the other end of the spectrum. Of course, we're all familiar with microwaves. We use the energy in the microwaves to energize our food, our coffee, tea, whatever the heck it is we're going to be zapping. And we zap it. And by the way, what is the purpose of the little grid? Have you ever thought about that? It keeps the radiation in. How? Yeah, but it's based on what characteristic of the microwaves? Yes, yeah. So it's designed so that they don't get out because of their wavelength. All right, kind of interesting. All right. So anyway, tables 12 or figure 12.3 is kind of interesting on that, and that's the lambda, the wavelength, my friends. Okay. All right. we already know that in addition to being characterized by frequency and wavelength, it travels at the speed of light. And that's what we're going to assume. Although that speed of light is diminished a little bit when it travels through air and things of this nature. And we will quantify it by differences on the spectrum. That is where it is a function where radiation or electromagnetic waves are quantified by their different wavelengths, their spectral considerations, and their directional. Which is a function of theta and psi. And we'll talk about that a little bit more today. Radiation is in order to be radiated, you have to be exposed to the radiation. You've all been to the dentist's office, and you've all probably had x-rays, and they put that lead apron over you and around your neck. That's to protect your thyroid and the rest of you from excess radiation, okay? And that lead has a tendency of blocking the x-rays, the radiation. And by the way, in most doctor's office where they have those machines or dental offices, one of the walls that the technician will stand behind has actually got a lead sheeting inside of it as part of the construction to protect them. They're the ones that really need the protection because they do it all day long. Yes?
Their vests also have a meter on the inside of them too.
Okay.
That read the radiation. I have a friend who does that.
Yeah. Because you want to make sure you don't get too much radiation. Madame Curie died, from radiation. Anyway, now let's do some of the stuff that's not too exciting, but which is necessary for our understanding, and that is some of the definitions. Oh, and you've all stood in front of a fireplace. You've all stood in front of a fire, and you realize if you stand right in front of the fireplace, you feel the fire. If you stand over to the side, not so much. And that's because radiation is very directionally dependent. Okay? Very directionally dependent. So we're going to have to take that directional component into account. All right. So let's do our definitions. All right, the first one we're going to look at is emissive power. E. And emissive power is the radiation energy rate which is emitted by a surface to all space, all right, over all wavelengths. So it is the radiation energy rate emitted, in other words, given off by a surface all space over all wavelengths. And it has units. It is mathematically described as E being equal to the change in the heat transfer divided by the per unit area, and it has units of watts per meter squared. Everything which has a temperature emits radiation. We emit radiation. Okay? Human beings. All right? The drink emits radiation. Okay? But it's also receiving radiation from everything else around it, which is radiating. So there's a whole lot of radiating going on. Yes.
Just over there, you said that in that deep void, like there's no gas or anything.
Right?
How can that be considered radiation if it gets in the air?
Oh, well, what happens in the case, may I borrow your drink for a second? What happens here, what's happening right now to China's drink is both conduction, convection, and radiation. All right? My hand is in contact with this glass. It's a solid, and the heat is transferring from my hand ultimately to the drink inside, because my hand is hotter. That's an example of conduction. We could solve that problem. Okay? At the same time, the glass, the cup is surrounded by air, which is more or less Poisson, except for the my talking. Let's say it's Poisson, and that is also transferring heat from the air, which is warmer than the drink, to the drink. But also, this glass is absorbing radiation from everything to which it is exposed, from every surface. Now, up to this point in the course, we have ignored radiation. And the conduction and the convection components for this particular glass are much greater right now under the circumstances because of the temperature differences. And you'll see that radiation, as we get into this, is a function of temperature squared, the difference squared to the 40. So there's not much differences between the temperatures here in this room and this glass. So it's not a big deal. However, it can be a big deal in many circumstances. It can be the biggest deal. Okay? And we've just ignored it for convenience so far in this course, simply because we hadn't gotten to this point. There's only so much we can do. Okay? So you got all three going on. In most cases here on Earth, in this type of environment, you have all three modes of heat transfer occurring at the same time. When you're in space, then you're just dealing with radiation, typically, if you're looking at the outside of it. But of course, as we all know, when it re-enters the atmosphere, you've got lots of things going on. Okay. All right. Let's see, where was I? Okay. This is known as just the general emissive power, but we also will talk about the spectral emissive power. And the spectral emissive power as you may, and we also refer to this as the spectral hemispheric emissive power, which is also known as the monochromatic emissive power. And that is the emissive power that's what? No. It is the emissive power which is emitted at a particular wavelength. Okay? It's the emissive power which is emitted at a particular wavelength. By the way, monochromatic means what? One color. You're all probably too young to remember monochromatic computer screens. Anyone ever seen one? Oh, they were sweet. Flashing green light. You know, we now have, I don't know, gazillion points on the screen. When they first came out, you could pretty much count all the points on the screen. You know, it's pretty horrible. But anyway, and that is symbolized with epsilon sub lambda, and that will be equal to the heat transfer which is given off, radiation heat transfer per unit area per wavelength. And the units on that are watts per meter squared micron. Okay. All right, so that's our first definition, emission of power. The next thing we're going to talk about is irradiation. And that's given the symbol G, or for spectral irradiation, the symbol G sub lambda. Okay? And this is defined, which is the radiation which is incident, radiant energy which is incident on a surface from per unit area from all space. So this is the radiant energy incident on a surface per unit area Oh, and I forgot this. Yeah, the definition here should have, to be precise, is also per unit area. So emissive power is defined as per unit area as well. I mentioned it here, but I did it right in the definition. So it's back to irradiation. It's radiant energy incident on a surface per unit area from all space. And the units on that are watts per meter squared, or for the spectral variant of irradiation, that would be the radiation incident on a surface per unit area based on the wavelength. That would have the same units but with microns. All right, now there's something here. We're going to use this. You've all heard the term that it was irradiated. We irradiate certain things to do what? And to kill certain things we don't want. Okay? Certain seed stocks and what have you are irradiated to kill certain types of pests. Well, we treat cancer with irradiate. We beam irradiation onto cancer. It's getting very much more sophisticated because what is one of the big advances recently in that area?
Yeah, they're able to target cancer cells.
They target things how? With advances in nanomaterials. They will inject into the patient's body materials which are then attracted to the cancerous cells, and the cancerous cells will absorb these, and then they act as a magnet for the radiation. Very, very, very neat. Very good. All right, but we've all heard the term irradiation, and that's what it means. Now let's take a look here at a surface. Here's your surface. And here coming in is this G sub lambda. We'll talk here in spectral terms for a moment. Now, this is a great time to talk about material properties, because material properties are very important. We are all familiar with material properties and how they can impact irradiation. It's a simple thing. If you're getting too much sun on the beach, what do? You put on sunscreen or a shirt or a beach robe or something like this. Why do we do that? It's very effective in blocking the solar radiation, which is coming at a relatively small wavelength spectrum from affecting your skin. Because what's the radiation really doing to your skin? Cooking it, yeah. One of my favorite things is One of my favorite Seinfelds is, you may be too young to remember this, all you've seen him in reruns, is when Kramer goes up to the roof and he uses butter. Do you remember that one? And he smells like turkey. People say, what's cooking? And he got a little too much sun. Do you remember, anybody else, do you remember that, Jen?
And the guy wants to, he's fantasizing about eating him.
Yeah.
He's cooked.
Yeah, yeah. So, anyway, that's what we're kind of doing. That's, of course, why microwaves work as well, because we are irradiating recooking materials. All right, so every material has radiative properties, and we need to understand these. We're going to use these a lot. So let's take a look at material radiative properties. Now I'll ask you all, when this radiation, this irradiation strikes the surface of this body, there are three things that can happen. Who can tell me what one of the things is that will happen? Yes? What? Pardon me? It can be absorbed. A certain amount of the radiation can be absorbed. So a certain percentage will be absorbed, and we'll draw this on here as alpha sub lambda times G sub lambda. And this alpha is one of the first material radiative properties that we're going to study. It is the absorptivity. And it is the percentage of radiation, the percentage of irradiation which strikes the surface, which is absorbed. Okay? Percentage of the radiation which is absorbed. What else can happen? Pardon me?
Reflected.
Part of it can be reflected. And that is given the symbol rho. Rho is called the reflectivity. This is a percentage of the irradiation that is reflected. Now, think about it. What color has a high reflectivity? What color has a low reflectivity? Black. All right. White clothing, typically in sunny environments, you'll find people wearing light colored clothing. There's a reason for that, a practical reason for that. White colored clothing does what? Pardon me?
Just like cars in Florida, if you want to white car versus a black car.
Because it will reflect the radiation. You got a black car in Florida, good luck getting into it, right? Yeah. All right, so that's reflectivity. So we've got reflectivity, we've got absorptivity, and what is the last one that we have? Transmission. What do X-rays do when you're X-rayed? They go right through you. They go right on through you. Now, some of them are blocked by certain things, and depending on the density of the material in your body, for example, bones stand up very nicely. X-rays don't do a great job on soft tissue, all right? They don't, they're too powerful in most cases to make any differentiation between soft tissue. So if you've got a if you've got muscle damage, or you've got some sort of lump or something like this that the doctors want to take a look at, they're typically not going to use X-rays, because X-rays are too powerful. They'll use other things such as magnetic resonant imaging, which is another form of electromagnetic pulsing, and or ultrasounds, which are ultrasonic, which is sound using sound waves. Okay? All right? So some of the radiation will in fact be transmitted right through the body. Now that is tau, the transmissivity. That's lambda. It's like a Greek language course. That is percentage of irradiation transmitted. And alpha plus rho plus tau has to equal 1. And if we are looking at the spectral variant of this, such as in this case up here, we would find that alpha sub lambda plus rho sub lambda plus tau sub lambda would have to equal 1 as well. Those are percentages, and they add up. All right, any questions on these material properties? If you look back in Appendix A of your book, you will see that there is a whole table back there on the reflective properties of materials. And we will use those as we go forward in the course solving some of the problems. All right? So now let's take a moment and take a look at the 2 different types of reflectivity or reflection that we are going to encounter in radiation. These are important. The first is what we know as spectral. Not specular. Specular radiation. And this is mirror-like radiation. Typical of a polished surface. Now what you see is radiation coming in, and being reflected where the angles would be equal to each other. We use this type of reflection. What is the most common, one of the most common uses of specular reflectivity?
Mirror.
Yeah, well, mirror is a highly polished surface which does reflect, but better than this.
Heat shielding?
Lights.
Tinfoil?
Yeah, one thing that you put in your car to reflect it from the.
Well, yeah, but that's actually, that is not a highly spectral. What is,
Oh, telescopes.
yeah.
Telescopes.
I never
Just
thought of that
one.
one. But what I'm thinking of is the parabolic mirrors that they use on solar collectors.
Yeah, the ones with the millions of mirrors.
If you look at,
Yeah, I watched how they polish it.
On the mirrors on telescopes?
Yeah.
Because they want to, what they're trying to do in the telescope is exactly what they're doing on the parabolic mirror, which is what?
Do you have any dust on it?
Yeah, but what are they
Focus it
doing?
all to one point.
Yeah.
They are intensifying all the radiation which is collected, and intensifying it on one point for the purpose of trying to interpret what's coming in from space. Or in the case of a parabolic surface like this, you'll see the tube in the center, and that tube is where a fluid will be carried, all right? And radiation will come in, and the mirror is designed so that all the radiation reflects in such a way that it is focused on this focal point. Now, another similar approach is out in Southern California, where they have these similar type of mirrors where they all turn and they reflect the radiation up to a tower. Have you ever seen these, the pictures? And they can achieve incredibly hot temperatures. Anyway, this is specular radiation. It doesn't happen in nature, by and large. I'm sure somebody will probably prove you wrong. I'd be happy to hear your example. But in nature, we have diffuse radiation. Okay? And this is when radiation strikes the surface and is scattered in all directions. This is typical of a rough surface. Diffusing the irradiation in all directions. All right, so in this case, we have our irradiation coming in, and portion of it is irradiated in many different directions. And that's called diffuse radiation. And that's what we have here in this room. I can't think of anything in this room which is secular in nature. All right. The last one that we'll attempt today is radiosity. And radiosity is given the symbol J or J sub lambda. All right, and it is defined as the total radiant energy rate the key word is total radiant energy rate, which leaves the surface. Again, per unit area, to all space. And it has the units of watts per meter squared or watts per meter squared micron. And here's what this looks like. You have your surface, and we know that the surface is irradiated. And we know that in most cases, unless the surface is completely absorbent, that a portion of the irradiation is reflected. But then we also know that the surface, as a function of its temperature, which we'll learn, what was in your reading last night, also has normal emissive power. So radiosity J is equal to rho lambda times G lambda plus E lambda. If we talk about total emissivity, or excuse me, total radiosity is equal to, J is equal to rho times G plus E. And that is where we're at right now. Now, the next two boards that I have is actually what you need to do your homework for tonight. But you can read ahead and give it a try. It's a very easy homework. Example problem in there helps a lot. Now, I have a special offer today. How many of you get hungry at lunch, but find yourself the starving college students unable to afford to go to the Dining Commons and pay? Boy, Brianna's giving me the eye like, what sort of research are you up to? How many of you would like to go and have lunch at the School of Engineering? At noon. I'm serious. No, you can't be excused.
I'm in.
I have 25 kids from the College Crusade of Rhode Island, high school kids, coming in. They're going to be scattering through the building here in a couple hours. And then afterwards, they'll be hungry and we'll take them to the Commons. I need 3 or 4 volunteers to go. You're eating on us, so you're going to go over in a big group. And then I need somebody who would be...